Hey there, calculus students. Thanks for checking out my video today on related rates. This is a very important calculus topic, tested on the AP test nearly every year. So today we're going to talk about a little bit of an introduction to related rates, and then we're also going to start solving some related rates problems as well. Okay. Our next application of derivative will focus on two or more rates that are simultaneously changing. We call these types of problems related rates problems. First, we're going to start just by conceptualizing how two rates can coexist at a time. So example 1 says, suppose water is poured at a steady rate into containers whose shapes are shown. Sketch the graph of the height of the water versus time for each one. So first, we just have a rectangular prism. Okay, so as the water is poured at a steady rate over time, the height will also continue to rise at a steady rate over time. It's a pretty basic one. Okay, but now we're looking at a different picture. Think about this one. As we pour it up to here, it's going to rise pretty slowly. But once it gets past that point, it's going to rise much more quickly. All right, so whatever that height is there, it's going to rise slowly at that height. And once it gets there, it's going to shoot up much quicker than before. So our height versus time graph may look like that. Same concept here. It's going to start off pretty slowly until we get to here. Then it's going to rise quickly until we get to here. And then it's going to be at the same rate as it was before. So we're going to have kind of like a three-piece piecewise function here. The first and the third should have the same slope. So a slow rise and a quick rise and a slow rise again. So maybe our height versus time graph looks like that. And the last one, even though it's circular, doesn't really make too much of a difference. The only difference is the smaller one is on the bottom this time. So it's going to rise quickly until it gets to this circle, and then it's going to slow down. All right, so maybe it'll look like this, a quick rise, and then a slower rise after that. Okay, now we're just going to practice writing rates mathematically. So how would I write that John is growing at a rate of 3 inches per year in calculus terms? Well, let's say we want to say John's height is some function h. Then we could say dh dt. So what does that mean? That height is changing as time is changing is equal to 3 inches per year. My mutual fund is shrinking by 4 cents a day. So let's call mutual fund M, and we could say dm dt is shrinking, so negative 0.04 cents per day. The radius of a circle is increasing by 4 feet an hour, so radius we'll call r, dr dt, increasing by 4 feet per hour. And volume is decreasing by 2 cubic inches per second. So volume will be V, dV dt, decreasing by 2 cubic inches per second. All right. With all that behind us, let's take a look at our first problem. A rectangle's length is increasing at a rate of 2 inches per second, and its width is increasing at a rate of 3 inches per second. Find how fast the perimeter is changing at the moment its length is 10 inches and its width is 6 inches. All right. Let's start by drawing a picture. How about a rectangle? We don't know its length, we don't know its width, but we know they're changing. And you can see here, we only want to label the things that are changing on our graph. We don't want to label things that are constant with a variable. Then we want to think about what's given to us. Well, we have the length is increasing at a rate of 2 inches per second. So we'll call that dl dt. And then we have the width is increasing at a rate of 3 inches per second. So we'll call that dw dt. What are we supposed to find? We're supposed to find how the perimeter is changing. So we'll call that dp dt. And we're looking for when that is L is equal to 10 and W is equal to 6. But those are not constants. Okay, those are not constants. Those are changing. The equation we're going to use. All right, so this is where you have to think about an equation that relates to things that we're talking about here. So the length and the width and the perimeter. So the perimeter of a rectangle is given by 2L plus 2W. With all that in mind, now we can finally begin to actually start the calculus of this problem. So I'm just going to copy down my equation over here. P equals 2L plus 2W. And I'm going to take the derivative of that with respect to time. So the perimeter is changing as time changes. Equals 2. The derivative of L is dL dt. The derivative of W is dW dt. So let's put in everything that we know. dL dt is 2 right now. dW dt is 3. So 2 times 2 plus 2 times 3 is 10 inches per second. All right, and then just like before, we want to write these answers out in sentence form. So a sentence could be, the perimeter of the rectangle is increasing at a rate of 10 inches per second when L equals 10 and W equals 6. Make sure you add that into your sentence. Part B says, now the rectangle's length is increasing by 3 inches per second and its width is decreasing by 2 inches per second. All right. So dL dt is 3, but dW dt is negative 2. Find how fast the area is changing. If we're supposed to find dA dt, but again, when L is 10 and W is 6. So our equation for area of a rectangle, length times width. So this time when we take our derivative, we are going to need to use the product rule. So dA dt equals L times dW dt plus W times dL dt. Okay, and then we just substitute everything that we know. We know that L right now is 10, dW dt is negative 2, W right now is 6, and dL dt is 3. So that would be negative 20 plus 18, or negative 2 square inches per second. Okay, so again, we write this out in a sentence. When L is 10 and W is 6, the area of the rectangle is decreasing at a rate of 2 square inches per second. All right, we have to make sure we mention when L is 10 and W is 6 because those numbers are not constant. We don't have to mention these numbers because these numbers aren't changing. So we always know those numbers are true. But since these numbers are changing, we have to mention those in our answer. All right, next example. A right triangle. A right triangle has sides whose lengths are changing. The short side is increasing at 3 inches per second, and the long side is decreasing at 5 inches per second. So here we have a right triangle. All right, we'll just call this the short side. We'll say S, and the long side we'll call L. What are we given? We're given that ds dt is 3 and dL dt is negative 5. We're trying to find the rate of change of the area when the short side is 30 and the long side is 40. So the equation for area of a triangle is base times height over 2, right? So base height over 2. Or if you prefer it this way, 1/2 base height. All right, taking the derivative of that, we would get dA dt equals 1/2 L ds dt plus S times 1/2 dL dt. So that's 1/2 times 40 times 3 plus 1/2 times 30 times -5, which would give us 60 minus 75, which is -15 square inches per second. Again, right out as a sentence here. When S is 30 and L is 40, or when the short side is 30 and the long side is 40, the area of the triangle is decreasing at a rate of 15 square inches per second. The next one, it's the same picture, except now we're going to add in the hypotenuse to it as well. How fast is the hypotenuse changing at the moment? So everything is the same here, except we're not looking for dA dt anymore. We're looking for dH dt. And the equation's not the same either. So what equation would relate these three together? That's just the Pythagorean theorem. So L squared plus S squared equals H squared. Okay? Taking our derivative, we get 2L dL dt plus 2S ds dt equals 2H dH dt. All right, and we should know everything there except for dH dt. Now, right now we don't have H, right? But we could find it pretty quickly. Knowing that L right now is 40 and S right now is 30, if we just do the Pythagorean theorem, we would get H right now is 50. So substituting in all the numbers that we know, we get 2 times 40 times -5 plus 2 times 30 times 3 equals 2 times 50 dH dt. Okay? So that would give us -400 plus 180 equals 100 dH dt. All right, or you can simplify this right now by getting rid of all the 2's. You can divide through by 2, make it a little bit easier to work with. Now we're talking about -200 plus 90 equals 50 dH dt. So that would be -110 equals 50 dH dt, or dH dt would equal -11/5 inches per second. Okay, so when the short side is 30 and the long side is 40, the hypotenuse is decreasing at a rate of 11/5 inches per second, or as a decimal, 2.2 inches per second. Okay, example 5. Talk about a cylinder this time. A right circular cylinder has a height and radius which are both changing. So let's start by drawing a cylinder. The cylinder has a circular top and a circular bottom. It also has a radius and a height that are changing. The radius is growing at 2 feet per minute, all right? So dr dt equals 2 feet per minute. The height is shrinking, so dH dt is -3 feet per minute. We are supposed to find the rate of change of the volume. So dV dt equals what? At the moment that the height is 10 and the radius is 8. So what equation is the volume of a cylinder? Hopefully you remember from your geometry days, that would be pi r squared h. Taking the derivative of this can be a little complicated. We are going to need the product rule again. So dV dt, if we let pi r squared be our first function, then that would be pi r squared times dH dt plus h times 2 pi r dr dt. And that should be everything that we need to figure this out here. All right, so pi, the radius right now is 8, so 8 squared. dH dt is -3. The height is 10. The radius is again 8, and dr dt is 2. And put that all together, we should get 128 pi cubic feet per minute. So when h is 10 and r is 8, the volume is increasing at a rate of 128 pi cubic inches per minute. The radius is decreasing at 4 feet per minute now. So dr dt is -4. And the height is increasing. So dH dt is 2. Find the rate of change of the surface area. All right, so this time we're looking for, I use capital T for surface area. Some people use something different, but I use capital T. You can use S or just A for area, that's fine too. And still H is equal to 10 and R is equal to 8. So the surface area of a cylinder is 2 times pi r squared, that's the two bases, plus 2 pi rh, which is the side of it. So taking the derivative of that, we get dt dt, d capital T, d lower t, of 4 pi r dr dt. And for the second part, we're going to need to do product rule again. So plus 2 pi r dH dt plus h times 2 pi dr dt. Okay, and that's it. Then we're just going to put all of our numbers in that we know. So 4 pi r times -4 plus 2 pi r times 2 plus 10 times 2 pi times -4. And that should leave us with -176 pi square feet per minute. So when h is 10 and r is 8, the surface area of the cylinder is decreasing at a rate of 176 pi square inches per minute. All right, at this point, we're going to stop this video here. We're going to continue these notes in a new video. But at that point, we're going to hopefully have the ability to try some of the next problems on your own. All right, so if you're looking for the second half of this video, it'll be